तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we are going to discuss error in the interpolating polynomial. Remember, we were discussing a polynomial that interpolates a given data, a set of data points. So today we will discuss what will be the error in this polynomial, that is, what is the difference this polynomial between the value this polynomial gives and the actual function value. That is what we will be looking at today. So we saw this yesterday, that polynomial Pn of x be a polynomial of degree n, which interpolates a real valued function f of x at x0, x1, x2, x3 up to xn. That is the function, this polynomial goes through all these points x0, x1, x2 up to xn. So now what we are interested in is actually getting a value in between x0 and xn, right. So any value which is not tabulated between x0 and xn. So let us say x is such a point and f of x is the actual value of the function at that point x between x0 and xn. Then Pn of x is the value that the polynomial gives for that x, right. So Pn of x is our interpolating polynomial, that is an approximate curve that passes through all these points, and x is a value somewhere in between which is not tabulated, and then Pn of x is the value of the polynomial at that x value, and f of x is the actual value of that function which we do not know. So the error is f of x minus Pn of x. So now we should try to estimate this error. Why is an estimate? Because we do not know f of x. That is why we need a Pn of x, right. So we do not know f of x, so we need to make an estimate for this error, f of x minus Pn of x. So the way that we do that is to say that let us consider a point x bar. Okay, let us consider some point x bar between x0 and xn, and we assume that we know the function value at x bar, that is, we know f of x bar, we assume for the time being, and then we can construct a polynomial of degree n plus 1 now, which goes through x bar, and we call that now as Pn plus 1 x bar, and that will be equal to f of x bar. And this is exact because we define the n plus 1th order polynomial as one which goes through x bar, that is, it takes the function value f of x bar at that point. Remember, the way we construct a polynomial of degree n which goes through n plus 1 points is to make sure that by making sure that this polynomial takes the function values at all the tabulated points. Now we added one more point to that tabulated set of points, which is x bar, and we construct a polynomial Pn plus 1 of x bar, okay, and that goes through that f of x bar. So that is, okay, and then we can define the polynomial Pn plus 1 of x as Pn of x, which was going through all the n plus 1 points. So remember, so Pn of x plus an additional term which will be now the n plus 1 term, right. The n plus 1 term will be j equal to 0 to n product x minus xj, right, and the coefficient of that will now contain x bar. And then we know that this polynomial Pn of x bar, Pn plus 1 will take the value function value f of x bar there, and then this would be Pn of x bar plus f x 0 x n x bar product j going to 0 to n x bar minus xj. So, now we see what we were interested in is actually f of x bar minus Pn of x bar, right. So, now from this we can see that the error f of x bar minus Pn of x bar is actually given by this term, right. So, it is given by this term, that is the next term in the polynomial of p order Pn plus 1. So, that gives us an estimate of the error. The error is now like the next term in the polynomial. Okay. So, what we have done, we had a polynomial of degree n which went through n plus 1 points, and we wanted to know what is the error in this polynomial, and the way we construct or we define this or estimate this error is by saying that let us say there is a point x bar which is in between this x 0 and x 1, and then we construct a polynomial of order n plus 1, okay, which goes through this point, and then we see that the error is actually the next term in the polynomial. So, therefore, for all x bar which is not equal to any of this n plus 1 tabulated points, the error is this. Okay. So, given this n plus 2 points, we can accurately determine the error in the interpolating polynomial of interpolating n plus 1 of those points. That is, let us say you have a set of n plus 2 points, okay, you have a set of n plus 2 points, and then you construct a polynomial of degree n, okay, and then it is going through this n plus 1 points of the n plus 2 points given to you. Then we can accurately estimate what will be the error, because we have an additional point here to estimate which allow us to estimate the error, because we can use that term to construct the next term in the polynomial and we can estimate the error. So, that is the idea here. But what happens if you do not know f of x bar at all? So, we do not have an additional point. So, then can we actually estimate the error still? Okay. It turns out you can still do that by using this what is called the mean value theorem, which tells us that given a function f of x defined in the interval a to b, and if that is k times differentiable, okay, then if x 0 to x k are the k plus 1 distinct points inside a and b, okay, within the interval a and b, then there is a value of x equal to I call zeta here, which is between a and b, okay, which is between a and b, and such that this function, this f of x 0 to x k to x bar, that is this coefficient of the n plus 1 term, is actually equal to the kth derivative of the function evaluated at that zeta divided by k factorial. That is what we are saying, trying to say is that the n plus 1 term's coefficient is actually equal to the kth derivative of the function at some value zeta, or we are saying that there is a value zeta which is between a and b, such that this coefficient is equal to the kth derivative of the function evaluated at that point divided by k factorial. Again, we do not know what the function is, so we do not know what the kth derivative is, okay, but we have an idea that this error will be of the order of the kth derivative. Okay, so, that gives us something. Okay. So, here is just an illustration of the mean value theorem, okay, which is explained a little bit more for the first derivative. There we are looking for the kth derivative, we look at for the first derivative. So, the mean value theorem basically states the following, that if a function f of x and its first derivative, so we are looking for the first derivative mean value theorem, and if it is continuous over an interval from xi to xi plus 1, then there exists at least one point on the function that has a slope, okay, designated by f prime of zeta, such that is parallel to the line joining f xi to xi plus 1. So, what is saying? It's saying that if there are 2 points xi and xi plus 1, okay, and there is a curve going through this point xi and xi plus 1, then along the curve, at least at one point, okay, its slope should be equal to, at least at one point, its slope should be equal to the line joining xi to xi plus 1. Okay. That is what basically that is saying. Okay. So, that is this point at this particular point theta marks the value of x at where this slope is. Okay. So this basically physically this means that if you travel between 2 points with an average velocity, okay, so if you travel between 2 points with some velocity, then you can compute what is the average velocity between these 2 points. Then there is along that travel, okay, at least one point you were traveling actually with that average velocity. Okay, so that looks trivial if you say this way, but if you are traveling between 2 points in some varying velocities, and then you compute the average velocity, then this theorem says that at least at one point along your travel, you were traveling with the average velocity. Okay, so that's the statement of this theorem, which is basically illustrated here. Okay, so that is illustrated here. So that's you are going from this point to this point, and you are traveling along this curve. Okay, and the average velocity will be marked by this this curve, right? So this curve connecting these 2 points, and you see that there is 2 points here. So what the theorem says that there is at least one point where the slope is parallel to this one, and here there are cases where there are two points where you have this slope parallel. And then given this theorem, you can actually estimate what that slope would be. Okay, you could just take that as r0 divided by h. That's the idea. Okay, so we can say that slope is actually given by r0 divided by h, or you could say what that r0 is by doing this. Okay, so that is now. This is just a simple proof for the derivative mean value theorem for the first derivative, and this can be extended to the nth derivative. We do not go through the proof of that here, but it is an extension of this arguments which takes it to the nth derivative. Okay, so back into this problem, we are saying that the estimate of the error is actually given by, or this coefficient is f of f, this kth derivative of f, and divided by k factorial. Okay. So that means what is the error term? The ENF x, which I call the error in the nth order polynomial at x bar. So now that will be given by f of x bar minus p n of x bar, which we just saw is f of n plus 1. There are k points, it is a kth derivative, there will be n plus 1 points, so go from 0 to n, which in this function. Okay, so here it will be n plus 1 divided by n plus 1 factorial, with j going from 0 to n, the product into x bar minus xj. So that it is a product of two quantities. One is the kth derivative divided by, so the n plus 1 derivative divided by n plus 1 factorial, and then a product of x bar minus xj. Okay, so that gives us some idea of how we could reduce the error in the polynomial. Right. One is that it goes as 1 by n plus 1 factorial, and the error is of the order of the n plus 1 derivative. So if you think the higher order derivatives are negligible along the curve which you are interested in, then we could construct a polynomial of order a larger n. Right. So we increase the degree of the polynomial, okay, to reduce the error in the thing. Okay, so that is one way, but that is not very convenient because that also increases this product, right. So we will have more terms in this product, and that is, as we saw earlier, is not a very good thing to do always, because you could have round off errors or other errors due to floating point operation coming in. Okay, so increasing the degree of the polynomial though might help, okay, it is not always good, because this term might work against us. That is the idea. And also increasing the n would mean more computer time. Okay, so So, a better method would be to actually try to reduce the second term, that is this term. Okay, well, why don't we reduce the value of this term, that is, remember we had two terms, a product of two terms here, which is this, and we can increase the degree of the polynomial and reduce this term maybe, but that might cost more computer time and maybe more errors in this term. So, another way to do is just to take a finite a small n, but try to reduce this value. So, what does it mean? Okay, so that would mean that we will choose the points x j in the product, okay, close to the x bar of interest to us. Okay. So, that is what we would do. Okay. What we would do is we will choose x bar, okay, at which the polynomial is to be evaluated, that is, this is x j's. So, x bar is a point at which we want to evaluate the polynomial. So, we will choose the x j's close to that x bar. So, that is one way of doing this, right. So, if you then we will reduce this error x bar minus x j. Okay. But then if you have a set of points going from 0 to n, then it is not possible to choose all the points close to x bar, because these points are given to you, these x j's are given to you, okay, and then x bars is a point at which you want to evaluate. So, what is the idea here is saying that let us not take all when you construct a polynomial, there is no need to take all the n points, all the n plus 1 points to construct a polynomial. Instead, what we do is we will choose a set of points which are close to x bar from the given set of tabulated x j values. We choose a set of points which are close to x bar and construct a polynomial of degree, let us say m, which is much smaller than n. So, that is the idea behind piecewise interpolation, polynomial interpolation. That is, for a given set of points, we keep constructing different polynomials for different intervals. For every interval, we will construct a polynomial and we will use that polynomial to evaluate x bar. So, that is the idea behind piecewise polynomial interpolation, and that is what we would be looking at. So, as a problem, probably one could look at this, that there is a construct a sixth order polynomial interpolating polynomial in the Lagrange and Newton's form to estimate the function x e to the power of minus x between 0 to 10. Okay. So, you take sample values at 1, 2, 3, 4, 5, 6 and 7. So, there are 7 points here. Okay. So, you could construct a sixth order polynomial, right. So, you have 1, 2, 3, 4, 5, 6, 7. So, sixth order polynomial. And then you construct a fifth order polynomial by just taking any 6 points, okay, and then you could estimate the error. So, there are two ways of estimating the error in this particular problem, which you probably should try out. That is, one is you know the functional form here. Okay. So, then you construct a sixth order polynomial going through the 7 points, okay, and evaluate at some value x, which is not tabulated here, and then compare it with the actual function and see what the error you get. Okay, and compare that with the error you can estimate by making a fifth order polynomial to go through this by choosing any 6 points in of the 7 values here, choose any 6 points and then make a fifth order polynomial and then find the difference between the fifth order and the sixth order polynomial at that value. Okay, that will be an interesting exercise to do. Okay, so coming back to the piecewise polynomial approximation. Okay, so what we do is, if you are given a set of points, let us say n points here, 1 to n. Okay, so and we have this function values between all these points. Okay, so what we do is for every interval, that is x1 to x2, x2 to x3, x3 to x4, etc., we will construct a polynomial. Okay. So, we know that these polynomials has to be kind of continuous across this, otherwise it does not look, it is not correct. So, we have to make sure that these polynomials are continuous between the intervals. Continuous means that it should satisfy the function values, that the polynomial which you construct for the interval 1 to 2 and the polynomial you construct for the interval 2 to 3 should match at point 2, right? And if possible, its derivatives also should match at point 2. Then we will make sure that it is continuous. Okay, so that is what we are going to do here. Okay. So, if you take the polynomial of degree 1, okay, if you say degree 1, which for every interval, okay, so we construct a linear function which interpolates between 1 to 2 and 2 to 3, then we do not have much of freedom, because the only thing we can do is to make sure that they match at the intermediate points. And if you take a linear function to interpolate between every interval, let us say 1 to 2, 2 to 3, then what we can make sure is that these polynomials match at the point 2, but its derivatives we can't do anything about it. But if it is more than n more than 1, then we have some freedom to adjust some parameters such that it is continuous. Okay. So that is the idea between the spline interpolation, that is you construct piecewise polynomials to go through all the intervals, and then so every interval you have a polynomial, and every interval you have polynomial of degree higher than 1. Okay. So we have some freedom to fix the derivatives, derivative continuity at the points where these two polynomials join. So that is the idea behind spline interpolation. So we would match the function values and its derivatives at in between points. We will see that now. Okay, so for example, let us take the simplest case of a quadratic polynomial. Okay. So just before that, I just want to show you a graphical illustration of this, and here is the case. So you have a set of points here given by blue curves. Okay, and you have a linear curve, a linear piecewise interpolating polynomial going through, and the red curve here is a cubic polynomial. Okay. So you have a linear function which interpolates between these two, and you can see that there are kings at this point because I can't match the derivatives, right. You can only make them go through all these points. But when you have a cubic function which interpolates all these points, you have a more continuous kind of line. Okay. So we have chosen for every point a polynomial of order 3 for this red curve, a polynomial of order 1 for the black curve. Okay. So that is what we have seen. Okay. So to get an idea about how do we construct this thing, the easiest thing maybe to think about is just look at a quadratic polynomial. Okay. So slightly better than n equal to 1 would be n equal to 2, right. So a typical quadratic polynomial which goes through xi is just written here. Okay. So this is a quadratic polynomial. So we will just see what how do we construct this polynomial piecewise. So I here would mean that something which goes from I minus 1 to I. Okay. So that would be the polynomial I. Okay. Or I to I plus 1, one of these things you have to take. So Pi, the I denotes the interval which you take, which is either I minus 1 to I or I plus 1 to I, depending upon what you fix it as. So we will see how do we construct a polynomial of this form. So we have 3 coefficients Ai, Bi and Ci for each interval. So we will have a set of coefficients, right. For every interval we have a set of coefficients, because every interval the polynomial is different. So for every interval we have a set of coefficients. So how do we determine these coefficients? First, of course, the polynomial I at xi. So we have constructed here the polynomial which goes from I to I plus 1 as Pi. So Pi is a polynomial which goes from I to I plus 1. Then we would say that Pi at xi should be the function xi, and the Pi at xi plus 1 should be function xi plus 1, right. Because that's the polynomial has to go through those 2 points, because it is interpolating between I to I plus 1, Pi is interpolating between I to I plus 1. So it should match the function value at I and I plus 1. And then we can also demand that the derivative of the polynomial at I, so this goes from I to I plus 1. Okay. So the polynomial, the ith polynomial which goes from I to I plus 1, okay, right. So this its value at I, that its derivative at I should be the same as the I minus 1th polynomial's derivative at I. Remember, the I minus 1th polynomial will go from I minus 1 to I. Right. So this goes to I and this also goes to I. So its derivatives at this point should match. So we have the 3 conditions at every interval. Okay. And these are the set of conditions which you could use to determine this polynomial Ai, Bi and Ci. Yeah, this coefficients of the polynomial Ai, Bi and Ci. We will see that now. So we have let us look at a simpler quadratic spline of this form. Okay, so f of I of x, which goes from I to I plus 1 as ai x square bi x plus ci. Okay. And then that is a polynomial at every interval. Okay. So, we have n plus 1 data points going from 0 to n, let us say, right, and that means there are n intervals. Okay. So, for each interval we have a polynomial. Right. So, that means we have 3n unknown quantities here to evaluate, that is the A's, B's and C's, 3n unknown quantities. For every interval there are 3 and there are n intervals, so there will be 3n unknown quantities. So, now we use the conditions that the function value at the boundaries of each of these intervals should match the polynomial value and its derivatives should match the two polynomials at the two adjacent intervals should match the derivatives at the intersection point. So, that is what we do. Okay. So, we have these conditions that the function the I minus 1th polynomial should take at I minus 1 the function value I minus 1, okay, and ith polynomial also at I minus 1 should take the function value I minus 1 given by I minus 1. Okay. And so, this is matching the two polynomials, and then that would give us 2 into n minus 1 conditions, that is 2n minus 2 conditions, right, for each interval 1. So, there are n minus 1 intervals. So, we get 2 into n minus 1 conditions. Remember, we have 3n conditions to solve, we have 3n unknowns to solve. Okay. So, we will come back to this again. We have taken only the intervals and the in between interior points, there are n minus 1 interior points, 2 conditions, and we have 2 boundary points that we have, that is 2, that is plus 2, we have 2n conditions. Remember again that we have 3n unknowns to satisfy, to get. Okay. So, then we use the derivatives. So, we match the derivatives at that points. So, we have the derivative in the I minus 1th interval and of the I minus 1th polynomial and the derivative of the ith polynomial matching at I minus 1. So, the derivative of the I minus 1th polynomial and the derivative of the ith polynomial will match at I minus 1. Okay. So, that gives us n minus 1 conditions again, because this is again interior points. Okay. At all the interior points we can match the derivatives of this polynomial. So, we have n minus 1 conditions. So, we had now 2n conditions before and we add n minus 1 conditions to it. So, we have 3n minus 1 conditions, but we still have 3n unknowns. So, we are short of one condition. So, we need to put in some extra information to decide this 3n coefficients, okay, and that is normally chosen as a derivative at the second derivative at one of the n points. Okay. Also, it would just say that we could take a derivative at one of the points and we would fix the derivative to be 0. Okay. So, the function values, and that will give us an additional constraint, and that has to be substituted into this thing. Okay. So, then once we have that condition, okay, then what we have is so what we have is this polynomial here given by a polynomial of this form, that f I of x is ai x square plus bi x plus ci, and we will have all the function values here. So, we have to have this extra condition, okay, which tells us what the second derivative at the boundary is to fix this one extra coefficient, which we cannot determine from the fact by demanding that the derivative of the piecewise polynomials match at all the interior points and the polynomials themselves match at all the interior points. Okay, the polynomials matches interior points gives us 2 into n minus 1 conditions, and the derivatives match at the interior points give us n minus 1 conditions, and the 2 n point values for the polynomials gives us 2 conditions. So, we get 3n minus 1 condition, we need 3n conditions, and we have to put in one extra condition. And once we have that condition, and then we can actually determine the polynomial and then we will have something like this. So, we will have for each of this interval, okay, a separate polynomial, and it is graphically marked it here. Okay. So, intervals 1, 2 and 3, Okay, for interval 1 we have polynomial with coefficients a1, b1 and c1, and for interval 2 we have a2, b2 and c2, and then interval 3 a3, b3 and c3. Okay, so that is what we would have. Okay, so this is just an illustration of what the polynomial, a piecewise polynomial would mean. Okay, so that is, we can actually express this, we can try to construct therefore this given set of such a polynomial for a given set of data points given here. Okay. So you could try that as an exercise, and then we would have 4 points, sorry 1, 2, 3, 4, 5, 6 points. So that means we have 1, 2, 3, 4 interior points and 2 boundary points. Okay. So we'll have, so we can equate the derivatives at this interior points, and so that will give us 1, 2, 3, 4 conditions. Okay, and this is the initial condition, which is one boundary condition which I had put in, and so we have this 5 equations here. Okay, and then we could have the function values, so the one polynomial in the interval 1, 2, 3, 4 to satisfy the function values at 1, 2 and 3, 4 as this. Okay, and then we know that we have the next polynomial also to satisfy the same function values at x1, right. So the interval, the polynomial going from 1 to 2 and the polynomial from going from 2 to 3 should satisfy the function value at 2, right. So that's another set of 4 function values. So that will be this. So that is polynomial going from 1 to 2 satisfying the function value at 2. Okay. So remember the previous one was the polynomial going from 1 to 2 satisfying the function value at 1, and going from 2 to 3 satisfying a function value at 2, etc. Okay. And this is the polynomial going from 1 to 2 satisfying the function value at 2. So we have 4 interior points here and then 4 function values, and we saw 4 into 4, 8 function values, and then we had 1 extra boundary condition, and then we had 4 derivatives to be satisfied. Okay, and then we have 2 boundary values to satisfy. Okay, so that gives us the full set of points, 15 points which we want to evaluate, 15 coefficients which we have to evaluate. Okay. So what's more commonly used in the spline interpolation is, instead of quadratic spline, would be a cubic spline. Okay, that is what more commonly used. Okay, and that's what is used always. Okay, and this we will find that it is much more easier to evaluate too. Okay. And the function, now we have 2 conditions. So that is, of course, the function, the polynomial going from I to I plus 1 would satisfy the continuity of the functions, that is pi at xi plus 1 should be equal to pi plus 1 at xi plus 1, right. We know that because it is be continuous across, or other way of saying it is pi of xi should be f of xi and pi of xi plus 1 should be f of xi plus 1, same as what we saw before. And then we have the derivative continuity, this also we just now saw, and now we also have the second derivative continuity. Okay, so we say that pi double prime, the second derivative of the function, should satisfy of the polynomial in the interval I to I plus 1 should match with that between I plus 1 to I plus 2 at I plus 1. So we have an additional condition here, and we have, because we have a cubic polynomial now. Okay. So now, since the pi's are cubic and the second derivatives are linear, okay, so that we construct this in a much more clever way. Okay, this polynomial, it's actually much easier to construct in this way, that we say that the polynomial is cubic, so its second derivatives are linear, and then such a linear polynomial, that is the second derivative of the cubic polynomial, can be written down in this fashion. Okay, so now you can see that this polynomial, that is the interval from I to I plus 1, okay, and the second derivative of that polynomial is given by f double prime of x, that is the second derivative of the function value at xi, some quantity which we do not know, because we do not know what the second derivative of the function value at xi is. We only know the function value at xi, but let us write it like this. So this is an unknown quantity into x minus xi plus 1 by xi minus xi plus 1, so like a Lagrange form, okay, and f double prime at xi plus 1, x minus xi plus 1, xi plus 1 minus xi. So now you can see that, let us evaluate this polynomial, the second derivative polynomial at xi plus 1. Okay, so then what we get is this, so at xi plus 1 we would get that as this goes to 0, xi plus 1 minus xi plus 1, this term goes to 0, and we would say that pi double prime at xi plus 1 is equal to f double prime at xi plus 1. So, the second derivative of the polynomial going from I to I plus 1 has f double prime at xi plus 1 as its value. Now, what will be the pi plus 1 double prime is? Pi plus 1 double prime would be xi plus 1 minus xi plus 2 x minus xi plus 2, x minus xi plus 1 divided by xi plus 2 minus xi plus 1, and this will be xi plus 1, this will be xi plus 2. And we can very easily see that pi plus 1 at xi plus 1 will again give us f double prime at xi plus 1. Okay, so, by this construction we have already satisfied that the second derivatives are continuous. Okay, by this construction of this second derivative, we have made sure that the second derivative of the polynomial at I plus 1, okay, xi plus 1, or for polynomial I at xi plus 1 and polynomial I plus 1 at xi plus 1 are the same. So, we know that. So, integrate now, if you integrate that linear polynomial twice, okay, we get a cubic polynomial, okay, and that is what I have done here. So, we have a cubic polynomial obtained by integrating that polynomial twice. Okay. So, we have now xi minus xi plus 1 cubed by 3. So, if you differentiate this twice, you get back that polynomial again. And then we have xi minus xi to power 3 divided by 6 here, and we have this additional terms, the linear terms, a is x minus xi and b into xi minus xi. So, we have this polynomial. Now, this is our cubic polynomial. So, we have a cubic polynomial, okay, which goes through which is interpolating between I to I plus 1, whose second derivative is continuous. Okay. So, we have already made sure of that. And now we can get this a and b values by saying that pi at xi plus 1 is equal to f of pi at xi is equal to f of xi. So, a is, so b is f of xi, you can see pi at xi, right, pi at xi would mean that this term would go to 0, and then we can construct this value from that. Okay. So, pi at xi is equal to f of xi. Okay. We can construct from that the b function from this, because this goes to 0 and we will have this goes to 0 and we will have only this and this terms left, and from that we can actually construct the b term. And then we have pi at xi plus 1, okay, going as f of xi plus 1, and from that we can construct the a, okay, because this will go to 0, this will go to 0, and we will have xi plus 1 minus xi plus 1 minus xi square by 6 into f double prime of xi. So, we can construct that polynomial. So, having done that, okay, so if we put in this boundary condition that the function value, so we have constructed this cubic polynomial by already in such a way that its second derivative continuity is guaranteed, and then we fix this some coefficients by saying that its function values should be, its value at the boundaries of those intervals should be equal to the function values. Okay. So, then what we have to fix now? Okay, so, now what we have to fix is this coefficients double prime xi and double prime xi plus 1. That is the only thing which is unknown in this now. Okay. We have fixed a and b by demanding that this goes through f pi xi plus 1 is equal to f of xi plus 1 and pi at xi is equal to f of xi. So, we have fixed that, okay, and now we need to fix these quantities. Okay. So, for that we have this so if you substitute all that, we get a polynomial of this form. Okay. So, we have the complete polynomial now, okay, which the only unknown in this polynomial now is just that f double prime at xi, f double prime at xi plus 1. All the double primes are unknowns. Okay. We do not know the second derivative of the function because we do not know the function itself. Okay. Now, we need to compute this f double prime of xi. Right. So, what we are going to use is that one more condition which is left to us, right. So, that is, remember in this equation we had this condition left, okay, that is pi at xi plus 1 and p prime at I plus 1 at xi plus 1 should be the same. That is, the first derivatives has to be continuous. So, now that is what we are going to use now. Okay. So, we can use that condition to get this coefficients which are unknown in this polynomial, okay, and then we have fixed the cubic polynomial. Okay. So, we will go ahead and look at that value now. Okay. So, this is the condition which says that the first derivative, I just taken the previous function, the pi of x, and find its derivatives, and pi at x I plus 1 and pi plus 1 at x I plus 1. The derivatives of these two, I just match them here. So, I get this equation. So, there is an equation which is, this is coming from pi at x, pi prime at x I plus 1, and this comes from pi plus 1 at x I plus 1. Okay. So, these two conditions which, and sorry, these two derivatives have been equated, and I have rearranged the terms into this form. Okay. So, you can see the right hand side of this equation is all known functions, and the left hand side we have this unknowns f double prime of x I, f double prime of x I plus 1, f double prime of x I plus 2. And this equation has to be written for all the n minus 1 interior points, and you notice that this, so you will have n minus 1 such equations to solve, right, and the right hand side of this equation is completely known. We know the function values, we know the xi values. So, the right hand side of the equation is known. These coefficients, this xi plus 1 minus xi, xi plus 2 minus xi, xi plus 2 minus xi plus 1 are known. So, what is not known is the derivative at xi, I plus 1 and I plus 2. So, each equation, okay, such n minus 1 equations, each of this equation will have 3 unknowns, and they are the second derivatives at I plus 1 and I plus 2. So, if you write down this equation from I going from 0 to n minus 2, okay, if you write down this whole equation, okay, and then you will get a tridiagonal matrix form. Okay. So, that is what you would get. Okay. So, we can use some shorter notations. Okay. We will use that, we say that second derivative is represented by zi's. Okay. And so, we will call, see in this equation we call this as di, okay, xi plus 1 minus xi as di, xi plus 2 minus xi as ei, and xi plus 2 minus xi plus 1 as hi, and this whole right hand side as ri. Okay. So, if I use this short notations, okay, so ri is the right hand side, and I use this notations, okay, 2xi plus 2 minus I as ei, and I plus 1 minus I as di, and I plus 2 minus I minus 1 as I plus 1 as hi. Okay. And then I can write down this in a very short form as di zi minus 1 plus ei zi plus hi zi plus 1 equal to ri. So, in this form I go from I going from 1 to I should go from 1 to n minus 1. So, that is what we will have. So, we will have n minus 1 such interior point equations. Okay. So, we will have it in a tridiagonal form. Okay. So, there will be, but we have n minus 1 equations and we have n plus 1 unknowns, okay, because right, we have n plus 1 unknowns, and but we have only n minus 1 equations. So, we need to fix this two remaining conditions. Okay. So, we have, remember what are our unknowns? Our unknowns are the second derivatives at every point, second derivative at every point, and we have n plus 1 points, right. We have n plus 1 points. So, we have n plus 1 unknowns. So, in the cubic spline interpolation, with the unknowns are the second derivatives at every point, and we have n plus 1 points, we have n plus 1 unknowns, but by this equation we are getting only n minus 1 such equation. So, we have 2 points to be fixed. We need 2 more equations, or we need to fix these 2 points, and these 2 points or these 2 values are fixed by demanding that f double prime of x0 and f double prime of xn are 0. That is, at the 2 ends we say the second derivatives are 0, okay, and this is known as natural spline. This is not the only way to fix this. You could fix it by some other way, but this is the standard practice, and it is known as a natural spline. Okay. So, when you see a standard algorithm, a program which gives you a polynomial interpolation, a cubic spline interpolation, it is most probably using this particular boundary condition, and that will be a natural spline interpolation. Okay. So, now let us say we have this problem which we discussed earlier. So, we have, if we want to find out a spline interpolation through this set of points, that is, we have one spline going from this to this, so that is 1, and then 2 and 3, 4, 5. Okay. So, we have to find out 5 splines, 5 cubic splines, so 5 cubic polynomials which you have to find out. Okay, so then as I said, the I is now is 0, 1, 2, 3, 4. So 0, so that is the intervals. Okay, so now we can construct the EIs, DIs, and HIs and RIs at this point. I have computed it for these points, these values. Okay, so EI, remember, is 2 times xi plus 2 minus xi, and DI is xi plus 1 minus xi, and HI is xi plus 2 minus xi. Okay, so I constructed all that here. And RI is the right hand side, which was a known function. So in terms of the function values, okay, that comes in on the right hand side. So in terms of this equation, this set of equations which I showed you in the here, okay, so these equations now can be actually written down for this particular data, for the set of data in this form. Okay. So we for every internal point interval, I can write down this equation, and then I will get this n minus 2 equations. Okay, so there are 6 values here. So 1, 2, 3, 4, 5, 6. Okay, so I have n is say n minus 2 such interior points, and I have this n minus 2 equations here. And I can solve this n minus 2 equations. Okay, you can solve them by elimination method. You can multiply, as you said, you could multiply this equation by d1 and divide it by E0, okay, and the whole equation, and then subtract it from this equation and multiply this by d2 and divide it by E0 and subtract from here, and that way you can eliminate this row. And similarly, by doing such elimination method, you can actually solve for all the values z1, z2, z3 and z4 here. Again, we have used z0 and z5 as 0. Okay, so we have used that condition. Z0 is 0 and Z5 is 0. Okay, so I can do that. Okay, and then so that means we have actually used this boundary conditions for also for this. Okay, so we can do this. Okay, and for this case, and actually solve this polynomial, and I can just quickly show you a program which implements this. Okay. So here is a program which would actually implement this method. So I have this tab again. I have this x, f, e. So I have the arrays declared here as x, f, e, d, h, and r. Okay, and the z. All these arrays declared here, and then I have put in all these function values into these arrays, x, f, and x and f. Okay. And then I have first constructed this E, H, R, D. So I have this E here evaluated as xi plus 2 minus xi into 2 for all the intervals, and Hi as xi plus 2 minus xi plus 1, and then Di as xi plus 1 minus xi, and then I computed Ri. So I have got all the known values from the data. So I made this table, okay, inside this with the program. So that's simple enough. So you can see it's very simple to construct this. Okay, and then I have done this elimination, as I said, eliminating this row. So I have taken the first row. I take the first row, divide that by E naught, okay, and then multiply it by D1, okay, and then subtract it from this, okay, and then divide this by E naught and multiply it by D2 and then subtract from this, and that way I can eliminate this row. So that's what's done here. Okay, so I goes from 0 to n minus 3. I have taken Di and divided by the Ei, okay, and then I have subtracted it from the rest of the thing. So that way I eliminate all that thing. Okay, and then I can back substitute this once I have eliminated all the D's. So I should actually write this. This is D3. So I have to eliminate D1, D2, and D3. So I have a. So there is a small mistake here. This should be D3. Okay, so this should be D3 here. So if I eliminate all these rows, okay, and then I have a simple equation here. From this I can solve for Z4. Okay, so I can, once I solve for Z4, because this whole row is eliminated, I can solve for Z4. Once I solve for Z4, I can substitute that here and solve for Z3. Okay, and then once I have the Z4 and Z3, I can substitute that here and solve for Z2 and then Z1. Okay, so I can solve all this by back substitution as it is known. Okay. So first task is to eliminate this row, this whole column. that is the D column. I eliminate this D column and then I have a modified value for E3, okay, and then a modified value for R3 because I am going to multiply this and subtract from this. And once I have done with that value, and then I can compute Z4 from that. And once I have the Z4, in this, now there is no D2 here, I have a modified E2 and a modified H2, and I know Z4 and a modified R2. So from that I can compute Z3. So I can go back like this, and that is what the next loop is implementing. So here is I have eliminated the D function values, okay, and here I am doing the back substitution. Okay, I start from the bottom, that is from n minus 3, and go all the way to 1, okay, and evaluate all the z values. Okay, so z equal to the first two values have been put in as z equal to 0, and z equal to 1 as 0. Okay, so that has been put in here, z equal to 0 and z equal to 1 as 0. Okay, and then I can actually construct my cubic polynomial, and that is simple. Then for every interval, now I am evaluating. What I am trying to do is for every interval I am trying to evaluate. Okay. So there is in this program, so I have now for every interval a cubic spline, okay, and I am saying that you take each interval, okay, going from I equal to 0 to n minus 1, okay, for each interval, and within each interval you take 5 points and try to evaluate the spline and that particular spline at that point. So that is what this is doing. Okay. And I will show you that. So here is the polynomial then. Okay, so again these points these are the points tabulated. This square points, the square symbols are the points which are tabulated, and this circular disk are the points which are evaluated using the cubic spline for each interval 1, and you can see that it is pretty continuous, and I can get this function values at every interval satisfied. So again, to summarize this point, this program, so let me again go back and then say that. Okay, so what we are doing here is we have the function values tabulated here, and I first construct these numbers, that is EIs, DIs, HIs and RIs, okay, which are as you saw has been given in this form here, okay, as here. So this can be easily programmed. Okay, and this RIs also can be programmed because all of them are known in this interval, and then we have this set of equations, and that is what is shown here. So we have this set of equations, and then in these equations I can eliminate this whole first array of points, or the DIs I can eliminate, okay, by. So if I write this, so all the Z1 coefficients, okay, the Z1 coefficients can be, this Z1 coefficient can be eliminated by multiplying this, dividing this row by E0 and multiplying D1, okay, and this Z2 coefficient can then be evaluated, can be eliminated by dividing this row which now does not have a D1, okay, by E1 and multiplying by D2, and the Z3 coefficient can be eliminated by multiplying this row, dividing this row which now does not have D2 and dividing it by E2 and multiplying by D2, etc. Okay. So you can continuously do this, and then you can eliminate all these rows, all these columns, and then you will have Z3 E4 is equal to R3 as the equation, all modified values of this coefficients E3 and R3, and then from that you can compute Z4, and then you can continue back substitution and then get the answers which we wanted to get, all the coefficients which we wanted to get. And then once you have the coefficients, we can construct this polynomial. Okay, once we have the coefficients, we can construct the polynomial. So we have this polynomial and all the function values, all the coefficients are then known, okay, and then we can construct this polynomial and evaluate the values in between every interval using the polynomial for that particular interval. So when you actually write a program, we need to be given some value x, we need to know what polynomial to choose, because we have now n minus 1 polynomial. So we have to choose one of the n minus 1 polynomials. Okay. So we have to know which interval it fits into, and then choose the appropriate polynomial, and then evaluate the polynomial at that value.
you